So today it is lecture number 33. So we will discuss in detail regarding least squares approximation and what are the application of this technique as well. Where we will try to the most important application you will find in data fitting or curve fitting. So outline of my today's lectures are the following. First, I will give a just brief recap of what we discuss about matrix of orthogonal transformation because it is needed to establish that least square approximation. Then I will go to discuss about least approximate solution and least approximate function. So both here you can talk about the solution directly, and here one function would least approximate function would come. That means if your system is suppose inconsistent, that system is not having any solution, then in that case you are trying to get an approximate solution. Among that approximate solution, you will look for optimal solution. But in linear algebra, you don't need to apply calculus. So here just from that orthogonality perspective and that other four fundamental subspaces, we will try to find least approximate solution. And with once we are having least approximate solution, then we will talk about the least approximate function as well. And at the last section of this lecture, I will talk about data fitting, and I will, if time permit, then I will also discuss what is the difference between data fitting and interpolation. So these two are very interesting, very famous technique to fit a curve. Data one is data fitting, another one is interpolation. It is a very classical technique of numerical analysis. So coming to recap of matrix of orthogonal transformation, in last class I had already discussed about how to find a matrix of orthogonal projection. So what you do with respect to a subspace, remember that you need to get a subspace. So if you are in R2, what are the possible subspace? Uh, there is only one non-trivial subspace, that one is line, and other are one is trivial, zero is trivial subspace, and R2 itself is a improper subspace. So generally, whenever I will call it a subspace, then subspace in what it must be a proper subspace. So with respect to a proper subspace, so in R2 there is only one proper subspace. What is that? Line. Line happens to be in that one-dimensional subspace, and R2 itself is a subspace, but R2 is a proper improper subspace in R2. So we won't take that kind of subspace. Suppose again similarly, if you are in R3, I had already mentioned that in R3, what are the possible proper subspaces? So proper subspaces happens to be line kind of subspaces. That means one-dimensional subspaces, and plane kind of subspaces. That means two-dimensional subspaces. So there are two kind of proper subspaces in R3, and again. Improper, R3 would be again improper subspace of R3, and 0 would be trivial subspace. So those are simple criteria, from high school. What is proper subset? Also, it is just a generalization of proper subset, an improper subset, and trivial subset. So here we for in R2, when you are in R2, or whether you are in R2 or Rn, you can take one-dimensional subspace anywhere. So here we are taking as a one-dimensional subspace. We are calling that line, and with respect to this line, you project every point of Rn uh, through this definition. That means projection of x with respect to L. We define it as this one is the length of the projection, and this is the direction of the projection, or simply you can say that magnitude of the projection. How you got it? You just taking dot product of x with u1, or that means you are projecting in the direction of u1, and this one is the projected part, or this is the length. So that's why this is a projected component of x in the direction of u1. So you had already seen that, and uh, we know that projection is a linear operation or linear operator. So once we are having a linear operation or linear operator or linear transformation, what we do, we need to find a corresponding matrix with respect to a standard basis. So matrix of this projection operator with respect to under a standard basis, directly you are getting by taking outer product of the direction u1. That means outer product of u1. If you take outer product of u1, directly you will get the matrix of the projection with respect to a standard basis. Similarly, if your subspace, that proper subspace happens to be m dimensional subspace. In that case, what would be the matrix? Matrix would be a m rank matrix. This is the matrix, m rank matrix here. And where how it is defined? It is defined through orthonormal basis of the given subspace V. So you know that orthogonalization I had already discussed. Apply Graham-Smith orthogonalization process and convert any non-standard basis into orthonormal basis. So you know that process. Through that you will get orthonormal basis, and after that what you do, M is just written as a sum of what these M, these M outer product of these M orthonormal basis element. So in that case, because rank of every outer product happens to be 1, matrix that you are getting due to outer product of a vector, the rank happens to be 1. So rank of this one is 1, rank of this one is 1, and rank of last this matrix, this one is also 1. So 1 plus 1 plus 1, it will go sum up to M. That's why rank of this matrix, this is the matrix of the projection over V. The rank of this matrix would be M. So you are getting a M ranked matrix of this projection operator. This projection operator. Okay, so these things we had already discussed in last class. So coming to today's lecture, so today we will discuss in detail about least squares approximation. So, coming how to define it. So I have given many here. Name of each concept. There would be if it is starting with C, that means it is talking about concept. If it is starting with P, then that one is talking about problem, and such kind of things would come here. And if there is a P, another P, then sometime P will talk about property as well. So orthogonal projection with respect to the subspace as a closest point in the subspace. So it is talking about, if you try to observe orthogonal projection as a conceptual concept, what does it talk about? It is talking about the closest point in the subspace. If you are projecting any point over a subspace, then you are getting a closest point in the subspace with respect to the given point. So that is the geometrical visualization of orthogonal projection. So we consider, so same thing. If you want to highlight algebraically, how can you? This I have written in the what in the framework of geometry. If you want to highlight in algebraic framework, how you can say that? So consider a vector x in Euclidean space Rn and a subspace V of this within this uh, Euclidean space Rn. Then the orthogonal projection of x, it is a vector in V that one is the closest point to x in the V. That means if you want to say all these word in the algebraic form, you say that norm of x minus projection of x, definitely it would be the least value for every V in V. Then you taking this, that means if you observe this infinity, you will see that when this will have least value, when here you are taking V is equal to projection of x. This a small v element you are taking from the given subspace V, then when it would be a smallest, when you are taking V equal to projection of x, that will give least value. So that's where it is talking about closest point. So I have also given a geometry of that you can talk about. So this is your any arbitrary point x in Rn. This one is Rn x. Okay, and we have taken here just visualization perspective. Our subspace V2 is what? It is a plane kind of subspace, 2D subspace. That means it is having two directions. So it is already visible here. Okay. Now what we do? We try to project x over this plane. So this is the projected part of x over the plane. It might be visible to everyone. Projected part. So projection of x over V. So you can look into that. Just try to find the distance of every point in this plane with respect to x. So if suppose you are taking any arbitrary point V from the plane or subspace V, so this is V. This point is V, and what is the difference or distance between x and V? This is the distance from the vector difference property. You can easily see that this is the difference between x and V, and this is the difference between uh, x and projection of x. So from the geometry also easily you can see that which one is uh, least value, which one is the closest value or least value, which one is the closest point? Anyone, would you like to answer? Which one is the closest? This is closest or this one is the closest? This name of this one, you can call it x minus projection of x. Anyone, would you like to answer? Ashwin, did you get it? Are you listening me? Abhishek, Abhishek, are you listening me? Uh, just try to respond. I asked one question, that which one is least having least distance, projection of x or any arbitrary element v from v, subspace v. Are you able to visualize that graph what I am discussing? Hello, Ashwin, I am listening you. I'm listening you. Just try to answer. I asked that. Hello, I'm listening you. Just respond my question. That okay, okay. I am going forward. If you are unable to answer, okay, fine. Then again, I'm explaining that here I'm asking one question, that are you able to see the graph? This graph? Just say yes or no. The graph is visible or not? Okay, I'm going forward. So here I would like to say that again. I'm recalling. Okay, so I'm asking that question. This factor is what? This factor is projection of x over the plane V. So it is already clear to you. Is it clear or not? So you are having this vector x is the given. X is given vector. So you are projecting this x over this plane. So uh, this vector we are calling it projection of x over V. Okay. So one vector you got at this projection of x over V, it would be in the plane V. Now you are taking another point V. Now with respect to these 2 points, just first try to find distance. So I'm just asking you whether this distance is the least or this is distance is the least. Which one is the least distance? Call this distance 1. This distance is 1 and this distance is 2. So whether 1 is least or 2 is least. Not getting. Okay, fine. From visual perspective, yeah, yeah, nice. That's I was willing to listen. So definitely the distance 1 is least distance. And what is 1? 1 we define it because how we define distance? We define it by norm. So this point we are calling it projection of x. And this point is x. So 1 is nothing. 1 is what? It is talking about norm of x minus projection of x over v. Okay, you can mute your microphone. Less than 1 is this one. Okay, we define algebraically like this way. And 2 is what? 2 is talking about this point is x and this point is v. So distance between x and v, how we denote it? We denote it by norm of x minus v, like this way. So same thing what I had already discussed. So through geometry also it is clear, and through algebraic definition it is also clear. So this projection of x is always giving a projection of x is always the closest point of x in the plane. If you are taking any point x, then projection of x always closest point in the plane. Okay. Now we consider an m by n matrix. Then what we are having one relation that kernel of A, it would be just equal to kernel of A transpose A. So it is very simple kind of relation. You can verify it. I'm not going to have algebraic proof of this one. Furthermore, if we are having m by n matrix and kernel of that matrix happens to be 0, then easily we can say that A transpose A is invertible. So these are very simple concept. During subspaces, you might have already seen that. Otherwise, if you need, then I will give a proof of that. If you are through example, we had already seen, and we will see further as well. Now I'm talking about next concept, that least square approximation of an inconsistent linear system. That means we are having a linear system ax equal to b, which is having no solution. Means it is inconsistent. And another way of inconsistent, that it is saying that b is not in the column space of coefficient matrix A. So that is the criteria of inconsistent. Okay. So this kind of system. So consider an inconsistent linear system ax equal to b. As this system is inconsistent, means that the vector b is not in the column space or image of A. Okay. So the same thing I had already written it here. Although this system cannot be solved, so we can't get analytical solution of the system, we might be interested in finding a good approximate solution. Good means it may leads to best or least solution. So we can try to find a vector x star such that A times x star, it is the closest point to B, or you can say that as close as possible to B. In other words, we try to minimize the error, that means norm of B minus AX. If you try to talk about from calculus perspective, we try to minimize this error, norm of B minus AX. That means we will project uh, B in such a way, that means this A times A x star, it would be the closest point of B in the specific plane. So you can that means in the image plane. So this is the scenario why you are not getting solution of this system ax equal to b. Suppose your that matrix it defines a column space, two-dimensional column space, call it plane. You are getting image of A or column space of A, it is a plane. So what you observe that the right hand side vector b, it is not in the column space of A. Easily from the picture it is already visible that b is not in the column space of A. So what you do, so that means it is a situation of being an inconsistent linear system. So what you will do, you will project this in the this column space of A. So this is the projected part, and this projected part is what we are calling it A times x star. A times x star in the plane B. And here we will try to find a solution with respect to this system. Now, that means we try to find x star, and A times x star is the projection of B in the column space of B. That is the concept. Or you can simply say, in the similar fashion, you can say that A times x star is the closest point of B, closest point in the plane or in the column space of A with respect to B. Second, third concept, we are calling it least square solution of a linear system. Here I will talk about solution. So consider an inconsistent linear system ax equal to b, where A is again m by n matrix, b is m dimensional vector, and then a vector x star. We will call it a least square solution of this system if norm of b minus x star is less than equal to b minus norm of b minus a x for every x in Rn. That means it is taking least value, or simply you can say that it is this one is what it is talking about, projection of b in the column space of A. That visual I had already discussed. So the term least squares and solution reflect that the fact we are minimizing the sum of the squares of the component of the vector b minus a. That means if you, it is a norm, and what norm? It is a Euclidean norm. I had already discussed that how we define Euclidean norm of a vector. Suppose x is a two-dimensional vector, or suppose n-dimensional vector. You have already taken it here. So how you define norm of this one? It is a square root of a sum of a square of component, sum of a square of component. So x is n-dimensional vector, so it will have n component, x1 x2 up to xn. So norm of x would be a square root of x1 a square plus x2 a square, plus it will go up to xn. Okay, and what you observe that here, whether you optimize this argument that be inside the square root, or whether you are going to optimize this one or a square with a square root of this one, it won't affect the optimal solution. Optimal solution would be same. That's why just to go and optimize this argument only, and that's why it is talking about minimizing the sum of the squares of the component of the vector b minus a. And geometry further here, again I had already discussed. That means you in general, this is talking about this vector. This one is any x in the plane, so in that perspective ax again it would be in the plane. So it is talking about again linear combination of column of a. So in that perspective it would be what, this longest this vector here you are taking b minus ax. This is b minus ax, and your ultimate job is that you have to minimize x in such a way you are willing to see this situation. This is the situation. That means you are willing to find a times x star. So here when you multiply, you will try to find x star in such a way you will get a times x star becomes projection of b in the column space of a. So this one is, you are looking for this least value. So that is the criteria geometrically. This one is the geometrically. If the system is happens to be consistent, in that case, what is the least square solution? It would be just exact solution of the system, and so you can say that error is zero. That means what is the concept of being consistent? Linear system. That means B is in the column space of A. That means B is not outside the plane. Especially for this situation I'm talking about, b is inside within the image of a or column space of a. In that case definitely projection of b with respect to the that this column space, it would be what, the it would be itself. If b is in the column space of write it like this way, column space of a or image of a, in that case projection of b would be the vector b itself. So that's way there is no there is no perpendicular part. That perpendicular part we are calling it also error. So error part is zero. So projection of b with respect to b, in this case it would be what, it would be b itself, and the error part or perpendicular part, that means uh, this part, it would be what, it would be zero. Or simply you can write it like this way. What would be a perpendicular part? How you will write it? You will write it b minus projection of b, and projection of b is also b. That means you are talking about b minus b. B minus b is what? It is zero. So talking about b minus b, and finally you are getting zero. So your error is zero. What is the norm of zero? Norm of zero is zero. That means you are getting zero. Now, main question is that how to find least square solution. So this one I have given name M01 method 1. M mean for method. So how to find this least square solution? So what you do? So here a vector x star, we will call it, it is a least square solution from the previous definition of the this system ax equal to b if uh, norm of b minus x star, it is least, taking least value for every x in Rn. That means it is satisfying this kind of criteria. Then we are saying that x star is the least square solution. Then how can you find? So simply just play with this definition. So I start with what does this definition is talking about. It is saying that a times x star is nothing. It is just projection of B in the column space of A. B is what? Column space of A or image of A. Both are same name. So A times x star is nothing, just it is a projection of B in the column space of A. So what does it imply? That it simply implies that B minus A star, where it will go? Definitely it will be what? It is talking about what is it? Is a B minus projection of B. And we know that if you are taking any vector, we can always decompose that vector in two forms. One part is we are calling it B parallel or B projection. Another part we are calling it B perp or B perpendicular part. So what B perp it becomes? B perp is nothing, just talking about B minus projection of B or B parallel. So B minus projection of B. So that is the concept. So definitely B minus A time x star is what? It is projection of B. So definitely B minus A x star, it would be perpendicular to every element of the column space of A. So that's way B minus A x star B, it belongs to V perp, that is orthogonal complement of B. And what is orthogonal complement of column space of A? Orthogonal complement of column space of A is nothing. It is talking about left kernel space. That means kernel of A transpose. So always I would like to say that if you if you are having any doubt, just recall again four fundamental subspaces of a matrix. So all these are related with that. That time I had already discussed in detail. So we had already seen that now B minus A times x star is now in the kernel space of A transpose. That means left kernel space. So what does it mean? That means if you multiply this B time A minus B minus A times x star with A transpose, then it will nullify. It will be nullified. That means A transpose B minus A x star, it would be 0, because it is coming null space of a transpose. That's why due to definition of null space, you are getting this relation, this null equation. And now what you do further, if you simplify it, what you are getting A transpose A times x star equal to A transpose B. What is this system? Is a consistent system, and that means it is a solvable system. And this system we are calling it a normal form or normal equation of the inconsistent system Ax equal to B. Remember that this one is inconsistent system. We are unable to solve this system, unable to find the solution of the system Ax equal to B. Why? Because it is consistent. So that's why we apply the technique from linear algebra, and through that we have converted into a consistent system. A system we are calling it normal equation, and the solution of this normal equation, that will give least square solution of the given linear system. Okay, so I think idea might be clear to everyone how to find least square solution. So if suppose kernel of the coefficient matrix A happens to be singleton set 0, then the linear system Ax equal to B, it has a unique least square solution. It would be given by x star equal to inverse of A transpose A times A transpose B. I had already mentioned that if kernel of A is singleton set 0, then it signifies that it implies that A transpose A is invertible. So from there, you can see that A transpose A, here kernel of A is suppose it is a singleton set having only 0 element, then you can say that A transpose A is invertible. So you can take it like directly, you can solve it and you can bring it this side. So that's why directly you are getting analytic representation of least square solution. This solution directly you are getting. So further, if you try to look into this value of this projection of B, then what would be that x star you have already got. So projection of B is simply you can say that it is talking about A times inverse of A transpose A times A transpose B. So what you do? So recall that again, orthogonal projection, finding the matrix of orthogonal projection. In last case, what I had already discussed in the in uh, during recap, what I had discussed, how to find a matrix of projection or orthogonal projection. So here, what you observe? So this is talking about, this is giving directly matrix of the projection. So here, this matrix is coming like this way. This matrix, if you take several B, suppose you try to generalize this result, and you are taking all those B which are not in the column space of A, and you can play with this B like in this way, several B, then definitely question would be that in order to get least square solution, what is the step? First step is definitely B is not in column space of A. So first step is that you project B in the column space of A. So project, if you do projection, so next question would be what is the matrix of that projection? So matrix of that projection is this one. Okay. So you got the matrix of projection as well. So it is having application. That's why I'm talking about this. From a computational point of view, it may be more efficient to solve normal equation by using Gaussian elimination method rather than finding solution directly from analytical solution. You know that directly finding inverse is really very hard job. So you have to find cofactor and other kind of determinant and many different kind of things. But solving Gaussian a system of equation with Gaussian elimination method, it looks very easy, and always you will get a fruitful result, and geometry is already visible to everyone. Okay, so coming to example, so here what we do, question is that we have to find a least square solution of a given linear system. So here question again I am recalling, find the least square solution of the system is this one, Ax equal to B, where A is what, it is a 3 by 2 matrix. That means there are, you observe two columns, and B is the given vector B, it is what, having a entry 0 0 6. So easily you can see that B definitely is not in the column space of A. So that's where this system is inconsistent system. That means this system is not having solution, any exact solution. So you have to look for least square solution. It is having B is not in the column space of A. Okay, so we will go for this square solution. So what is the geometry? Also, I will talk about next question is what is the geometrical relation between the projection of B. That means what is that? That one is A times x star and the given vector B. So we need to compute directly analytical solution. We had already discussed in last slide. So from there we can compute directly least square solution x star. It would be what? It would be inverse of A transpose A into A transpose B, and A is already given here. A is a coefficient matrix. You just do simplification, and this one would be your after simplification. What you least square solution you will get? It will, you will get this one. That means first coordinate is -4 and second coordinate is 3. So also easily you can see that -4 3. It is talking about two coordinate, and the column of space of A, what it is having two direction, because A is having two independent column. That's why it is having two directions. That's why you are getting two coordinate for solution. This solution X. But in general, if you, okay, and now if you are talking about geometry, so in order to talk about geometrical relation between A times x star and B, so you have to compute A times x star. So if you compute A times x star, it would be what? It is this factor that is having entry -1 to 5. So as A times x star is the orthogonal projection of B onto column space of A, and B minus A times x star, it is coming is 1 -1 A is indeed perpendicular to that column space, two column vectors of A, or simply you can say that column space of A. And here you can see that geometry. This is your x star. Geometrically you can visualize like this way, and this one is your A times x star. This one is your given vector B. This plane is what? It is a column space of A. All all the geometry are given here. Okay. So whenever you solve such kind of problem, always try to draw geometry as well for better visualization. Now, I will talk about one more important concept that it is talking about least square approximation and the matrix of orthogonal projection. So consider a subspace V of Rn, and basis of that V is what? Uh, Having m number of basis element, that means V is m dimensional subspace of Rn, and these are the V1, V2, V2 up to Vm. All these are basis element of V, and so by taking these basis element as a column, we are forming a matrix A. That means this matrix, what is the dimension of this matrix or size of this matrix? Size of this matrix is n by m. Then the matrix of orthogonal projection, it can be directly given with the help of the previous result. That means uh, previous result means how you simplify A times x star, and x star was what? X star was inverse of A transpose A into A transpose. Okay, so and you just multiply it with A. So matrix of that would be so like this way. So in total, you can say that matrix of orthogonal projection directly you can get it like this way. So one benefit of this representation is that you don't need to uh, transform your any given non-standard basis into orthonormal basis by using Graham-Smith orthogonalization. You are skipping that result and directly you are getting your matrix of the orthogonal projection. So matrix of orthogonal projection directly you are getting like this way. Later when I will discuss in next module regarding singular value decomposition, that time I will term it as a pseudo inverse. And with the SPD also we will calculate this pseudo inverse. Okay, if the vectors v1 v2 up to vm, that means basis element of the subspace v happens to be orthonormal, then simply what it implies that A transpose A is identity matrix. Why? Because A would be a orthogonal matrix due to orthonormality of vi's, and the above formula it will be just simplified to what? It will simplify to A into A transpose. Same thing we had already discussed in the uh, in last lecture. So now what we do, find the matrix of orthogonal projection onto now here one question is coming. So we have to find the matrix of orthogonal projection onto the subspace of R4 spanned by the following two vectors V1 and V2. So clearly you can observe that V1 and V2 are not orthonormal vectors. These are independent but not orthonormal. So first we have to get coefficient matrix that A matrix A that whose column are coming from V1 and V2. Now directly just implicate this formula, and through that easily you will get the matrix of the projection, orthogonal projection. So what it would be, just simplify this product of matrices. So it is a little bit complicated, but it is saving the that tedious process of Graham-Smith orthogonalization. Although Graham-Smith orthogonalization is having very interesting kind of geometry. That one is a pure geometrical technique, but here just it is a very algebraic kind of things. It is a pure algebra and just do calculation of all these matrices, and finally you will get the matrix of the orthogonal projection. So directly in just in one step solution you are getting it here, but here you have to find the inverse. Okay, it is already 45 minutes. Other things we will discuss in next class. In between, if you are having any question, you can ask regarding attendance.